trig functions of angles beyond the first quadrant. Okay, so we were in example 3, which was to okay. Let's see, I'm going to switch to gray. Hopefully gray is good and legible here. Which example 3 was to find the exact value of each. That, okay, how does that look? Does anyone say or think that that's not very legible? Or is it okay for you guys? If no one speaks up, I'm going to assume it's okay. All right. It looks pretty light here, but maybe it looks darker for you in the camera. Okay. We did A, B, and C. I think I marked D is where we left off. So tangent of 210 degrees. We want to find the exact value. That means not using a calculator. That means finding the ratio of the sides given this function and this angle. Okay, so we had to draw the angle. 210 degrees. So drawing the angle was maybe a little tricky. We had to think about, you know, where the 90 degree, 180 degree, and 270 degree and 360 are for reference. So if I know that this is 180, then I'm going to go 30 degrees past in order to draw that 210 degree angle. And by the way, why am I drawing it? Well, because I need to know what quadrant I'm landing in. So I'm in quadrant 3. Okay, so I'm in quadrant 3, which tells me that since 210 degrees is in quadrant 3, tangent of theta, whatever theta is in quadrant 3, should, well, no, sorry, I'll say tangent of 210 degrees specifically. Tangent of 210 degrees should be positive, right? Because we know tangent is positive in the third quadrant because tangent is the ratio of y over x, right? And if y and x are both negative down here, then y over x, the negatives cancel and we end up with a positive. All that just to say that tangent, that whatever answer we get here should be positive. Now, the other reason we needed to draw it was to find that reference angle, which I'll call theta bar here, assuming theta is 210 degrees. Theta bar in this third quadrant here, trying to get back to the x-axis, right, from the terminal side of this 210 degrees back to the x-axis. I know that should be 30 degrees. So I need to consider a 30, 60, 90 in order to find the correct ratio of sides that the tangent function should output. So find the quadrant, draw the angle, find the reference angle. Reference angle tells you what kind of triangle to draw, which is what I'm on now. That's my little 30 degrees there. I know that this is my special reference triangle with a 1, 2 square root of 3 sides, 2 being the hypotenuse, 1 being the short side. The short side is across from the tiny angle. Okay, remember that. Okay, and tangent outputs for this particular reference triangle, tangent outputs opposite over adjacent, like the vertical line over the horizontal line, the y over x, which is 1 over square root of 3. How does that translate over here to tangent of 210 degrees? It's exactly the same, except I need to say tangent is positive. Oh, so that's fine. I don't need to change the sign. So tangent of 210 degrees should be 1 over square root of 3. And then if I wanted to rationalize the denominator, I could say, by the way, 1 over square root of 3 times square root of 3 over square root of 3 is going to be square root of 3 over 3. So if I really wanted a nice clean answer with a rationalized denominator, then I would have tangent of 210 degrees is equal to square root of 3 over 3. Okay. Now, part E, I think I already gave you all of these. I gave you guys most of these. So did anyone do, I don't remember. I think I wrote them all down for you. Did anyone do the tangent of 300 degrees? And if you did, what did you get for your answer? Okay, so first thing I would do, I guess I'll do my work here, is I would draw the 300-degree angle. So first step is to draw the 300-degree angle. I know that that's 90, 180, 270. That's 270 down there. I need to go 30 degrees past 30 degrees past that 270 mark there. So there's my 300-degree angle, 300 degrees, 300-degree angle all the way in the fourth quadrant. My trig function is tangent. Tangent of 300 degrees, since we're in the fourth quadrant, is going to be negative. So keep that in mind, it's going to end up being negative. My reference angle, theta bar, well, if this is a little 30-degree angle here, and by the way, how do I know my reference angle goes there? Because it should go from the terminal side of the original angle back to the x-axis. So in quadrant 3, that means it falls back on itself on the original angle. In quadrant 4, that means it completes the rest of the revolution. It means different things in each quadrant. We looked at that last time. So here, theta bar is going to be 60 degrees. Because I know I went 30 degrees past this vertical line, so to complete that, it should be 60 degrees. Okay, so now I'm thinking about tangent of 60 degrees. So I know, well, rather before I even think about tangent, I'm thinking of the 60-degree angle. That's going to be one of these reference triangles. It's actually the same as this one, just oriented a little bit differently with that short side on the bottom, like that. Tangent outputs for this, for oriented this way, the square root of 3 ends up on top. So tangent of 3, sorry. Tangent of 60 degrees from this reference triangle is opposite over adjacent, square root of 3 over 1, which is just square root of 3, right? So this, together with knowing that tangent should be negative in this quadrant, tangent of 300 degrees should be negative square root of 3 over 1. So just negative square root of 3. So hopefully this is making sense, that you could see how these things are coming together here. Any questions so far? Okay, let's go to F. I'm going to go through this one a bit quicker. Sine of negative 330 degrees. Okay, first thing, draw the angle. First thing is to draw the angle, noting that it's a negative angle, so I'm going to be rotating clockwise. Okay, negative 90, negative 180, negative 270, all the way around to negative 330. So that's 60 degrees past this negative 270. Okay, there I am. My reference, oh, let me write that angle down. So that's negative 300, oops, negative 330 degrees, negative 330 degrees. So my reference angle here from the terminal side, completing the revolution in this first quadrant. So last time I said that in the first quadrant, the angle and the reference angle are the same, but that's only if the angle is positive. So this is an angle that ended up in quadrant 1 from rotating it's negative, right? It rotated all the way around. So this is a different kind of situation. Theta bar is completing the revolution here. It's going to be 30 degrees. Your reference angle shouldn't be negative. Okay, it shouldn't be negative. So you won't say negative 30 degrees. The reference angle is coming from the x-axis, meeting the terminal side. Reference angle should be positive. Because the point of the reference angle is just to get you back to a nice little acute triangle. Nice little acute triangle, one of those special triangles. So here it is. I've already drawn this one. Now I need to think about sine in the first quadrant. So sine of negative 330 degrees should be positive because it ends up in the first quadrant. Sine is positive up there. And then sine of 30 degrees from my triangle is opposite over hypotenuse, 1/2. So sine of 330 degrees, negative 330 degrees is positive 1/2. So the sign not changing there because the sine function is positive in the first quadrant, which is where this angle, the original angle, ended up. Okay. G is secant of -5 pi over 4. Secant of -5 pi over 4. Maybe we should quickly note, if we're not comfortable with these radian measurements, we can quickly note that -5 pi on 4. I know pi on 4 is a 45-degree angle. So if I have 5 of those, that's 90, 180, and a little bit more, 225 degrees. Or you could just use that, multiplying by 180 over pi, that thing we learned all the way at the beginning about converting radians to degrees. And by the way, it is still negative. That negative carries over. So we have a negative 225-degree angle. So let's draw it. Now I know you're worried about that secant function, right? Like, what do we do with that? But let's not worry about that. Let's draw the angle first. Draw the angle. So can someone tell me, let's see, Bailey, what quadrant would this angle end up in?
Would it be quadrant 3?
Quadrant 3?
Yeah.
Let's see. So negative 225 degrees. So this is negative 90, right? If you can see what I'm doing, so negative 90 gets me from fourth quadrant into the third, and then negative 180, and then I'll go a bit past that, 45 degrees past that into, in what quadrant am I landing in?
2.
Yes, 2. So negative, so that's my negative 225-degree angle. Okay. And my reference angle here, theta bar, oop, I didn't leave myself room. I'll write it over here. Theta bar is going to be, in terms of degrees, it's this from going negative from x-axis over to here, flipping around, is negative 180. And then it went 45 degrees past that. So my reference angle is going to be 45 degrees in terms of degrees, but we should really, it's okay to change things into degrees as an intermediate step, but you should really stick with the however that angle was given in the problem. So in other words, I'm saying my reference angle should be pi on 4. And I'm going to do that just to make you guys become more comfortable with the radians here. All right, so now I need to start thinking about the trig function. I need to, first of all, what is its sign? What is the sign of the secant function in quadrant 2? So what is the sign of the secant function in quadrant 2? To answer that, we note that secant of theta is just equal to 1 over cosine theta. So it shares a sign, so it has the same sign as cosine, has the same signs as cosine. So that means if cosine, which is controlled by the x values, right? Cosine is the x over radius or adjacent over hypotenuse. Cosine is controlled by the sign of the x values, which are negative in quadrant 2. So since cosine of theta is negative in quadrant 2, then secant of theta is negative in quadrant 2. Okay, so whenever I ask you to do something like this, one of these problems for secant, cosecant, or cotangent, you need to think of it back in terms of this little reciprocal identity, right? So secant corresponds to 1 over cosine. Cosecant corresponds to 1 over sine. Cotangent corresponds to 1 over tangent. And they're going to share the signs with whatever the trig function, you know, is they're the reciprocal of. Moreover, since they are because of this little reciprocal identity, since cosine of theta is equal to adjacent over hypotenuse, then secant of theta is going to be the reciprocal, the multiplicative multiplicative inverse of this. In other words, flip it upside down, hypotenuse over adjacent. That's going to be useful when we draw our reference triangle, which we have kind of postponed for now because we've been talking about secant for a bit. But that'll be useful in a moment to recall that since secant of theta is the reciprocal of cosine, it's 1 over cosine, whatever the ratio that cosine outputs, which is adjacent over hypotenuse, secant just flips it upside down. Cool. So we need our reference triangle now. Now, where is that coming from? The reference triangle is coming from the reference angle of pi on 4. So just for room, I'm going to cover that up. Sorry if you were still copying that. I'll uncover it in a moment. Okay, so from theta bar, our reference angle, we have this pi on 4. Let me draw it right. It's supposed, the pi on 4s and the 45-degree triangles are supposed to be isosceles, meaning their legs are the same. So let me kind of, that's approximately. Okay, so the angle is pi on 4, and the sides are, I forget how we write it, 1 square root of 2, or if you like, you can write them as square root of 2, square root of 2, and 2. If you want to just go ahead and scale it up so you don't have to worry about rationalizing the denominators, this is fine. And in fact, that's what I'll use. And recall that this is just a 45, 45, 90. I'm just writing it in terms of pi on 4 instead of 45 degrees. All right, so now what I want to do is find secant of pi on 4. So secant, and I'll use this one with the scaled up triangle. Secant of pi on 4 is going to be equal to hypotenuse over adjacent. The multiplicative inverse, the reciprocal of cosine. Hypotenuse over adjacent, so that's going to be, okay, I'm actually going to have to rationalize it back because I flipped, anyway, okay, that's fine. So hypotenuse over adjacent. Okay, which by the way, if I just rationalize the denominator, square root of 2 over square root of 2, you're going to think I'm so dumb for doing this, but it's just going to end up back at this triangle. Okay, so in the bottom, square root of 2 times square root of 2 is 2. Then the 2's cancel, and I just get a square root of 2, which is exactly what I would have gotten if I did hypotenuse over adjacent for this triangle. Whatever, they give the same thing. Sometimes you have to rationalize the denominator, sometimes you don't. If you're smarter than me and think ahead of time about what your answer is going to look like, then you'll know which triangle to use, but it doesn't really matter. You know how to rationalize denominators. It's no problem if you need to do it. All right. So secant of pi on 4 is square root of 2. But what I really want is secant of negative 5 pi on 4, which looks a lot more scary, but I know now that it's going to just be square root of 2, except that the negative 5 pi on 4 angles in quadrant 2, I'm sorry, I'm moving around so much. Secant is negative. Oh, that's supposed to be a 0, not a theta. That's 0. Secant of theta is less than 0, in other words, negative in quadrant 2. So there's my secant. Secant of negative 5 pi on 4 is negative square root of 2. So the reference angle and the reference triangle gets you almost all the way to the answer. The only other thing is you have to know where the angle is, which quadrant, so that you can say what the sign of your trig function is going to be in that quadrant. There are 3 more, but I'm going to skip them. Does anyone have, I think I'm remembering now that I did write them down. So does anyone have any questions about H, I, or J, or want me to do any of them? The ones that I wrote down from last time. Cotangent of 210 degrees, tangent of 840 degrees, and sine of pi on 2. Okay. Okay, if there are no questions, that's fine. We can skip those and move on to the next thing. Here is a classic problem that you will be asked. Homework and exams. Example 4. Classic problem where you're given a trig function output, but not the angle. So remember, a trig function takes as input an angle and outputs a ratio of sides. So what if you're given the output, what is it, of some trig function like this, but not the angle. And I also tell you that the angle is in quadrant 3. And I say, find the other trig functions, the 5 other trig functions. So I'm looking for sine, cosine, already have tangent. So sine, cosine, secant, cosecant, and cotangent. So find the other, so it's 5 trig functions because there are 6 altogether. Okay, what do I have? Tangent of theta equals 2/3. What does this tell me? Tangent of theta equals 2/3 tells me that the ratio of the opposite side to adjacent side is 2/3. 2/3. That doesn't necessarily mean that when I draw my triangle that the side is exactly 2, the opposite side is 2 and the adjacent side is 3. It just means the ratio of them is 2:3. But that's enough for us to work with. That's enough for us to work with. The ratio of the opposite side to adjacent side is 2/3. But the other trig functions deal with the hypotenuse too, right? Not just the opposite and adjacent. In fact, with this, with tangent of theta equals 2/3, we can go ahead and find one of the other trig functions, which is cotangent, because cotangent shares a sign with tangent, meaning that cotangent would also be positive, and all it does is flip it. So I can go ahead and say, without any other calculation, that cotangent of theta is going to be 3/2. But what about sine, cosine, secant, and cosecant? So let me write that down. I immediately know that cotangent of theta is equal to 3/2 since cotangent of theta is just 1 over tangent of theta. So if tangent of theta is 2/3, then 1/2 is 1 divided by 2/3, flip it around, fraction arithmetic, I'm kind of brushing under the table, but you end up with, just flip it, you just flip the fraction, right? It's 3/2. But again, what about these other trig functions that need the hypotenuse? So how do I find the hypotenuse? Well, the Pythagorean theorem, right? I've kind of been dancing around it here, but you've probably already thought about it. If I give you the two legs of the triangle, the opposite side and the adjacent side, or at least the ratio of opposite to adjacent, then you know that you can find this hypotenuse just by the Pythagorean theorem. So I'll quickly move through that. So h is equal to the square root of 2 squared plus 3 squared, which is going to be the square root of 13. 4 plus 9 is 13 under square root. Cool. Now I've got it. I've got the hypotenuse. So that means that I'm going to write some stuff down, and then I'm going to ask you what I might be missing here. Sine of theta is opposite over hypotenuse. So 2 over, no, notice I'm leaving a little bit of room right there. 2 over square root of 13. You may already know why I'm leaving room. Cosine of theta is equal to adjacent over hypotenuse. Again, going to leave a little room. 3 over square root of 13. Now, what about cosecant of theta? Well, cosecant is just the reciprocal of sine, so that'll be square root of 13 over 2. Again, leaving some room because I need to decide if they're going to be positive or negative. So these are not my final answers yet, but it's very close. And secant of theta, finally, is the multiplicative inverse of cosine, so just flipping that square root of 13 over 3. Now, which one of these should be negative? Does anyone want to venture a guess? If we know from the beginning of the problem that theta is in quadrant 3, tangent and cotangent are positive in quadrant 3, but which trig functions are negative in quadrant 3? So, Karina, which trig functions are negative in quadrant 3? Does anyone have an idea about which trig functions are negative in quadrant 3?
Cosine?
Yeah, and sine, right? Oh, okay. Karina may have sent a chat. Yes. Yeah, okay, Braden did. Yes, sine and cosine. That's right, sine and cosine. Because sine is controlled by the sign of the y value, and y is negative in quadrant 3. Cosine is controlled by the sign of the x value, and x is negative in quadrant 3, so that means they're both negative. That means that if sine is negative, so I'm adjusting that here, that's why I left a little room for a negative sign. If sine is negative, then that means cosecant is also negative because they're reciprocals of each other. And also I said cosine is negative, and that means secant is also negative. So there's my 5 trig function, well, 4, and then I already wrote cotangent, so just to complete the list down here, I can say cotangent is 3 over 2. This is a classic kind of problem you'll be given. You'll be given a trig function that the output of some trig function. It might be tangent, it might be sine, cosine, whatever. From those, you'll build the rest of your triangle by either finding hypotenuse or possibly having to find one of the legs. That'll let you build up the rest of your trig functions for the most part, but then you have to go back and look at where theta is to determine which of your trig functions should be negative. And in this case, sine, cosine, cosecant, and secant are all negative, but my cotangent and tangent are both positive. Okay. Okay, are there any questions about this one, or would anyone like to see another example about this particular type of problem? Or do we feel like we're good? Okay. Alrighty then, let's move into section 5.4, which is inverse trig functions and right triangles. Inverse trigonometric functions and right triangles. What is this? I don't recall what that has to do with. 1 second. Oh, right. Okay. Okay. First, quick note about the upcoming exam, which is on the 3rd of February, so a week from today. Note about exam 1. It's on February 3rd at 1:30 p.m. in Ayers Hall, room, I believe it's 355. Let me make sure. I got it written down. Yeah. Oh, not 1:30. Sorry, our class is 1:45. Sorry, 1:45. In room AH 355, Ayers Hall 355. So sorry, the exam is at the normal class time, 1:45 p.m. Okay, it will cover ideally sections 5.1 through 5.6, but I don't know whose idea it was to put us on such a tight schedule, especially with starting off on a holiday. Okay, it was my idea, but I definitely didn't plan good. So it's going to cover sections 5.1 through 5.4. Okay, now what about the law of sines, which is section 5.5, and the law of cosines, which is section 5.6? Those I'm going to, we're still going to cover them, but since they kind of can stand alone, I mean, there's definitely a reason they're in this chapter. I'm actually going to put them all the way at the back of the semester, probably. So I will adjust due dates, because right now 5.5 and 5.6 are due on the 3rd along with the rest of these. So I will adjust due dates for 5.5 and 5.6. So you'll still get to see the law of sines and law of cosines basically extend, well, it allows you to solve any triangle. Like given any angle, any side, you can solve any triangle, solve all the missing sides and all the missing angles. The law of cosines is pretty much the Pythagorean theorem on steroids. Like it looks like the Pythagorean theorem, but it's got this crazy like extra term on the back. And it's really nice. So definitely not going to just omit it from our curriculum because they're really important. So instead, I'm going to put I'll decide which exam they will end up on, because they'll be on an exam, probably not exam 2, either exam 3 or the final exam, and whichever one I look at and decide would be, which one would be easier to add these to, I will make that adjustment for the due dates, and yeah, I'll adjust accordingly. So the exam 1 will not cover sections 5.5 and 5.6. So that means we're in the last section here, which is good because it's a long section, and I am going to get into it now. Inverse trig functions and right triangles. First, not worrying about the right triangle part, just thinking about inverse trig functions. Okay. So we've been calling these things trig functions. We've been calling, I'm going to be talking a lot for the next like half hour, just so you know, not doing a lot of examples. Try to sit through it, try to pay attention and take in what I'm saying. even though you're not going to have a chance really to do examples for a little bit. So we've been calling sine, cosine, tangent, these 6 trig functions, we've been calling them functions. We've been calling these functions, but we haven't talked about any of the usual stuff you talk about with functions, like domain, range. We haven't even talked about pictures of them yet. That'll be chapter 6. So let's start talking about them as functions, and let's start talking about their domains and ranges. Now recall, the domain is just the stuff that's allowed to be plugged in. So theta, in this case, is the representative here for domain. The range is the stuff that the function is allowed to output. Okay. So from what we've seen, do any of these trig functions have restricted domains? So in pre-cal, you may recall that restricted domains came from like square roots of negatives. You can't have that, and division by 0. Right, so that was when you had a restricted domain, but most functions were pretty nice in pre-cal. They didn't have restricted domains, most of them. Like polynomials, like x squared, x cubed, stuff like that, they don't have restricted domains. Do these trig functions have restricted domains? Well, that is not a clean-cut answer. Some of them do, some of them don't. Have we seen any yet? Well, I think I've alluded to a few of them, but let me just go ahead and write it down. Sine of theta and cosine of theta have no restrictions on their domains. What's a fancy notation way of saying that? For these functions, for sine theta and cosine theta, their domain, which is theta, represented by theta, is unbounded. It can go from negative infinity to positive infinity. Unbounded domain. You can show that as an interval too. You can say negative infinity up to, not brackets, with parentheses. Negative infinity up to infinity. Okay, so sine and cosine have unrestricted domains. You can plug in negative 10,000 into the functions and they'll take it no problem. What about tangent? And then also, what about the cofunction, these reciprocal functions too? We'll talk about those. For tangent of theta, we do have some restrictions. Do we know where they're coming from? Recall that tangent, in terms of x and y points, gives a ratio of y over x, right? So this is in terms of coordinate points. So like just thinking about a coordinate point on the graph x, y. So this side being y, this side being x, and this side being r. Then we saw how sine of theta is y over r, cosine of theta is x over r, and tangent of theta is y over x. And when I say y over x, I literally mean coordinate values for coordinate points. So since tangent gives a ratio where x is in the denominator, are there any angles you can think of where x is 0? So what angles correspond to an x value that is 0? So think about an angle. You can start all the way at a 0 degree angle. Moving along, when will x be 0? If I put a coordinate point, if I follow a coordinate point along, at what angle will the x be 0? Does anyone have any ideas? What angle will x be 0? Where is x equal to 0? It's along the y-axis. So what angles lie along the y-axis? The 90-degree angle, right? And also the 270-degree angle. 90 degrees and 270 degrees. And in fact, any other angle, so 90 and 270, and also any other angle that wraps all the way around. And if it lands on the y-axis, then that's bad. That means x is 0. That means tangent will be undefined at that angle. Okay, so tangent is undefined at angles where that x will end up being 0 because it gives us division by 0. Undefined at theta equals 90 degrees, 270 degrees, and other odd multiples of 90. So not like 180, that's fine. 180 is fine and 360 is fine. So not all multiples of 90, but odd multiples. So this is 90 times 1, 90 times 3, 90 times 5, 90 times 7, etc. And I'll say odd multiples of 90 degrees. Now, in terms of radians, since we like to be comfortable with radians too, 90 degrees is pi over 2. 270 is 3 pi over 2. It's easier to see the odd multiples happening here. 5 pi over 2, 7 pi over 2, etc. Odd multiples of pi on 2. It's easier to see when I say multiples. That's easier to see with in terms of radians. You literally see 1 pi on 2, 3, 5, 7 pi on 2, 9 pi on 2, etc. Okay, so tangent is undefined at those angles, And you can confirm with your calculator. If your calculator's in degree mode, go tell it to do tangent of 90 degrees and it'll say no. It refuses to do it. Okay, so we see that so far sine and cosine have unrestricted domains, and tangent has a slightly restricted domain. It has holes in its domain. So for tangent, what can we say? Sorry, for tangent of theta, domain has, let's just say, holes at odd multiples of pi on 2. Odd multiples of pi on 2. Once we have pictures in chapter 6, we'll connect back to this and it'll be really nice to have a picture. You can always go and graph these functions too if you'd like, and you'll see that tangent theta has this asymptotic behavior. It like shoots off to infinity at these pi on 2 values. It kind of freaks out when you try and get it to plug in pi on 2 or any odd multiple of pi on 2. It blows up to infinity or negative infinity. Whereas sine and cosine are fine. They'll at pi on 2, they either output 1 or 0, no problem. Okay. Now, let's just worry about these first 3 trig functions for now. We don't need to worry about the domain and range of these reciprocal functions. We'll worry about them if we need to, kind of on a case-by-case basis. So let's just work with sine, cosine, and tangent. By the way, though, it wouldn't be hard to figure these out, but it's fine. It's fine. Let's keep going with sine, cosine, and tangent. Let's consider the ranges. So we have the domains of our classic 3 trig functions, sine, cosine, tangent. What about ranges? Okay, have we seen anything about the ranges? Okay. I'm just going to go ahead and give it away. Sine and cosine cannot output anything. Now, you may not have noticed this yet, but if you go back and check, you'll see that it's true. Anything larger than 1 or smaller than -1. -1. Why? Consider that sine of theta is equal to the opposite side of a triangle, of a right triangle, over the hypotenuse. And of course, cosine of theta is equal to the adjacent side over the hypotenuse. Now, here comes a fact that you already know. The hypotenuse is always larger than the other sides, than the legs, right? Than the opposite or adjacent sides. Than the legs, right? Than the opposite. So what does that mean for the these outputs of opposite over hypotenuse, adjacent? Well, let's just consider this then. Then what does it mean for opposite over hypotenuse? If just stepping back from trig, thinking about fractions, thinking just about fractions, sorry, 1 second. Okay, thinking just about fractions, what does it mean if the hypotenuse, the denominator is larger than the numerator? Then it's a proper fraction and that it's less than 1, right? And similarly over here, for just by a the same argument, if denominator is always larger than the numerator, like 2/3 or 1/2, then it's a proper fraction and it's less than 1. That's why the range of sine and cosine is bounded by 1. And I could make this, if I flip this over and make everything negative, it's the same kind of argument if you just slap a negative sign on it. So that's why these trig functions are bounded, well, sine and cosine rather, are bounded between 1 and -1. So what about tangent? Or well, let me say it this way. So sine for sine theta and cosine theta, the range, capital R, is just going to be from -1 to 1. Or we can say it, you might see it this way. If you look it up online, you might see it. The entire function, the output, this is the output of sine of theta, is bounded between -1 and 1, and also cosine is bounded between -1 and 1. This is its range. Okay, now let's consider tangent. So I'm going to kind of follow a similar argument here to see if we can get a similar bound off of tangent. Consider tangent of theta is equal to opposite over adjacent. Now, is there any kind of restriction about the legs of a triangle? Like last time I said, or not last time, right here, I said that the hypotenuse is always larger than the opposite or adjacent sides, right? It's always, the hypotenuse is the longest part of the triangle. But can I say the opposite side is always larger than the adjacent or vice versa? No, right? I can't say anything like that. There is no bound on opposite side could be huge, right? And adjacent could be very tiny. There is no bound here. There is no bound on this fraction. So just as a picture to show you what I mean, the opposite side could be ginormous. Like we could have a very extreme triangle like this, where the opposite side is huge and the adjacent side is tiny, and that would give us a huge numerator over tiny denominator. That's going to be a very large number. And likewise, I could have a very small number making my adjacent side huge and my opposite side very small, if this number is huge and this number is very small, then the tangent is getting very, very tiny. So there's no bound. There's no bound on this fraction. In fact, the range, so for tangent of theta, the range is unbounded. So I could say negative infinity up to infinity, or just as an interval notation. I don't know why I keep putting brackets on that. Negative infinity to positive infinity with parentheses around it. All right, it'd be nice if we had a table of this, so let me write that down. We still haven't started talking about inverse functions, but we're getting there. Okay, so for sine and cosine, the domain was unbounded, negative infinity to positive infinity. The domain for tangent was not necessarily bounded, but it had holes, right? So we'll just say that in words. Don't want to worry about, don't want to worry about how to notate that with intervals as holes at odd multiples of pi on 2. All right, now the range for sine and cosine were both bounded between -1 to 1. Okay, and tangent of theta, its range was actually unbounded. There it is, domain and range all in a nice little table there. Good. Finally, we are ready to start talking about the inverse of these functions, the inverse of these functions. So let's finally, well, actually, no, we're not. We got to talk about what an inverse function is first. So consider what an inverse function does. So we're going to review this. An inverse function does. Now I'm going to get you guys back involved because I know I've been talking for a while about this domain and range of sine, cosine, and tangent. Does anyone remember, especially if you took me for pre-cal, I emphasize this a lot. Does anyone remember what an inverse function does in terms of domain and range? What does it do to domain and range? Ji-Cheng, you took me for 112. Do you remember what an inverse function does? I remember. Yeah, go ahead.
Yeah, I remember how a graph is
So think about domain and range. What does an inverse function do to domain and range? It swaps them, right?
Yeah, swap them.
It flips them around. Okay, so an inverse function swaps domain. So what an inverse function does, it swaps domain and range. Okay. Okay, so can I just say the inverse function and literally like flip this table around, right? Can I do that? No, because we need to do something where we restrict. I want to make sure I'm saying this right. 1 second. We have to restrict the domains here in order to make these invertible. So what do I mean by that? An inverse function swaps domain and range, but an inverse function must also be invertible. It must also be 1-to-1 or injective. I think we say 1-to-1 in pre-cal algebra. It must be 1-to-1. Okay, what does that mean? So let's recall what 1-to-1 means. That means there is only one input for exactly one output. This means there's only one input for exactly one output. So real quick examples from pre-cal of a function that is invertible. So f of x equals 2x plus 3. I can invert this, no problem. It's 1-to-1, meaning that if you drew the graph of it, it passes the horizontal line test. There's a lot of stuff we can say about it. This is invertible. And let's leave it at that. An example of something that's not invertible, so it's sometimes easier to talk about something that's not invertible than something that is the x squared graph. Why is this not invertible? This is not invertible. Why? Because if we give it an input, if we give it, I'm getting to a point here, I promise. If we give it an input of 2, it gives an output of 4, okay? Duh, an output of 4. 2 squared is 4, sure. Also, so that's no problem. If we give it a -2, it gives a 4. It gives a 4. That is a problem because for a function to be 1-to-1, to be invertible, it needs to be 1-to-1, and only one input needs to exist for exactly one output. So when we have a situation like this, where a function takes in a 2 and it gives us a 4, and then it can take in a different value and give us the exact same output, then it's not invertible. It's not invertible. It does not have this nice 1-to-1 relationship with its domain and range. Remember, domain is input, range is output, so it's not 1-to-1. Our trig functions are not 1-to-1 as they are, as we understand them. Our trig functions are not 1-to-1, so they are not invertible. So they are not invertible. Okay. Example of that, sine of 45 degrees. This is like one of the problems from earlier. Sine of 45 degrees is going to end up being square root of 2/2. And sine of 135 degrees, which would be this is like example 3 from the beginning. I would draw my reference angle, blah, 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 work through all that. It ends up being positive. Get the exact same answer. So 2 different inputs going to the same output. That's what happened here. 2 different inputs going to the same output. That means it's not invertible. That means it's not invertible. So what do we do? This section is called inverse functions, right? Inverse trig functions. So what do? We will restrict the domains of each trig function. So we won't allow our sine function to go to 135 degrees. We're only going to let it go to a place where it will. We're gonna keep it in a small area domain, so that it will not give us any repeated values. So we will restrict the domains of each trig function so that they are 1-to-1. An example of this is if you did want to invert, remember that function I gave back here, x squared. We can talk about a partial inverse of that. So if you recall, like x squared is a parabola, right? You know that. And I can talk about the square root of x as a function. And remember, an invertible function like rotate, it rotates the graph and whatever, so we don't need to worry about that. But what I have to do is I have to only keep part of the parabola if I do want to talk about its inverse. So we've already done this in pre-cal where you restrict the domain of a function in order to talk about its inverse. We just may not have said it in that way. So we're going to restrict the domains of our trig functions so that they are 1-to-1. And here's what we're going to, here's the picture of the domains. Sine of theta is going to be restricted to the first and fourth quadrants. It's going to have a new restricted domain from here to here. So this gets rid of, so you know how sine is positive here and here, so we don't want this quadrant, and sine is negative here and here, so we don't want this one. So just keeping these two allows for all of the signs that's, well, positive and negative that the sine function can output. So our domain is going to be from down here, which is negative pi on 2, if I start, if I consider it as a negative angle, up to pi on 2. Okay, cosine of theta in its restricted domain, I want to make sure I get where it's positive and where cosine is negative, but only one of each, right? So right there. So its domain is going to be 0 up to pi. Notice it's the same size. Its domain is the same size as this one up here, but it's just oriented. It's like scooted over, right? And then tangent of theta, its restricted domain. Now remember, tangent had those issues at pi on 2 and negative pi, all those odd multiples of pi on 2. Oops. Okay, fine. I'll draw all these little arrows. They're not critical right now. Its domain is going to be similar to sines, except we don't want to actually include those actual angles there. And what I mean by that is we're just going to have parentheses on our domain instead of brackets. So everything in between these angles, but not including the endpoints there. Now we are ready to write down the corresponding table. Where's the corresponding table with our domains and ranges for our sine inverse, cosine inverse, and tangent inverse functions. So here they are. Sine inverse of, 1 second. Well, yeah, I'm going to say x here. I'll explain why it's x and not theta in a second. Cosine inverse of x and tangent inverse of x. Let me just get these domains and ranges down. And then we'll talk about a little bit more about the notation here with the x and what a sine inverse function, well, what the inverse functions do in general. Okay. Now, let's get these here for reference. Now, did I need to restrict the range of any of my any of my original functions? So remember, these are the base functions and these are the inverses, so I should expect the domain and range to be swapping here. Did I have to restrict range? All of that stuff I was talking about, no, it was all about restricting domain, right? So these get copied over right in here. The domain of sine inverse is negative 1-to-1. The cosine, domain of cosine inverse is negative 1-to-1, and the domain of tangent inverse is negative infinity to infinity. Now the domain gets copied here, and now the range of the inverse functions, but the restricted domains, right? So the restricted domain for sine was negative pi on 2 to pi on 2. That was the restricted domain for sine, so domain is going into range now. The restricted domain for cosine, that now becomes the range of the inverse function, was 0 to pi. And the restricted domain down here for tangent, for the tangent, we restricted the domain to negative pi on 2 to pi on 2, not including the endpoint, so that becomes the range of the inverse function here. There it all is. All together there. So we see that they do swap from here to here, the tables swap, but the domain here had to be restricted in order to become an appropriate range up here to make sure that the functions are acting right. Okay. Now, what does a inverse trig function do? And why am I using x instead of theta? Well, because a trig function takes in theta as an input into like, I'll just use cosine theta as an example here. The cosine theta is the function, theta is the input, and it outputs a ratio, right? A ratio of sides of a triangle. Right, I've been saying that in words, but here's a little diagram for it. In particular, cosine gives adjacent over hypotenuse, right? A ratio of sides of a right triangle. Then the inverse function is now going to take in a ratio of sides of a right triangle, which typically will just be denoted as a single number because, you know, any ratio can just be written as like a number if we want to. So we'll say x is now our new input into a inverse trig function, and it's going to output an angle. So cosine of theta equals x means that cosine inverse of x is equal to theta. This opens up a lot of options for us here, a lot of potential for problems in practice and exercise problems, all sorts of things we can do where now we're going to be, instead of giving you an angle and asking for the ratio of sides, I'm now going to be able to give you just some number or a ratio of sides and asking you for the corresponding angle that created that ratio of sides. Okay, let's do example 1, and then we'll be done for today. And we'll finish 5.4 and probably do some review on Monday. All right, so example 1 here. Finally getting to an example that you can practice. Oh, where's the rest of... Okay, evaluate each expression. A sine inverse of square root of 2 over 2. Okay. So what does this mean? We're looking for some angle, so we need theta, because that's what we're looking for, theta, so that sine of theta yields square root of 2 over 2. Do we remember what angle yields a ratio of sides like that? It's a special angle. Does anyone remember? Any guesses? Okay, so the angle that outputs this special ratio of sides, if we recall that 45, 45, 90, don't the sides look like 2's and square roots of 2's? So this is a 45-degree angle. So based off of this, theta could be pi on 4, which is 45 degrees, or it could be 3 pi on 4, because sine also yields square root of 2 over 2 for 3 pi on 4. So this is 45 degrees or 135 degrees. But we restricted the domain of sine. We restricted the domain of sine, in other words, i.e. we restricted the range of inverse sine. Sine inverse. So we restricted the range of inverse sine to, what did we restrict it to from our table? The range needs to be restricted to negative pi on 2 up to pi on 2. Only one of these angles falls into this interval here. Is it pi on 4 or 3 pi on 4? And it's definitely got to be pi on 4. So sine inverse of square root of 2 over 2 is just equal to pi on 4. Pi on 4 there. Not 3 pi on 4 because that's outside of the range that we allow for sine inverse. 3 pi on 4 is outside of this range. Okay. Part B. Got several parts. We got E parts here. Part B is cosine inverse of 0 degrees. Oh, sorry, not 0 degrees. Whoops, we're looking for an angle, sorry. Cosine inverse of 0. So I've given you a little table about these kind of special values when, so, you know, angles that output zeros and ones. So we are looking for theta so that what happens? Cosine of theta is equal to 0. Cosine of theta is equal to 0. What angle gives us 0 for cosine? Then this is just something you got to kind of be comfortable with. You got to start to remember that the angle we're looking for is pi on 2, or where else does cosine yield a 0? 3 pi on 2. Or equivalently with the degrees, 90 degrees or 270 degrees. But we only want one answer here, right? We only want one answer. We've restricted the range of cosine to be from 0 to pi. So which one of these falls into 0 or pi? Definitely the pi on 2. So the angle we're looking for, cosine inverse of 0, should be pi over 2. It's tricky stuff because basically we're doing what we did, you know, what you learned last time and last week, doing it in reverse now, but with this extra stipulation that you've got to find the correct angle that's in the right range. Okay. C is tangent inverse of square root of 3. Okay. We are looking for an angle. Wait, let me say we are looking for theta so that tangent of theta is equal to square root of 3. By the way, these are all going to be the special angles. Which special angle gave us a square root of 3 as an output from tangent? Now, that's quite a question, right? So how do you deal with that? You should first of all remember that square root of 3, that's coming from the 30, 60, 90 triangle. So just plop one down. Just plop one down. Let me draw it a little bit better. Plop one down and say, okay, that's square root of 3, that's 1, and that's 2. Tangent is supposed to be opposite over adjacent. So I have this backwards here, right? It should be this one where the 60 degree angle is down here. That's the 1, that's the square root of 3, and that's the 2. In other words, I'm looking for an angle like 60 degrees. 60 degrees. But I also know that tangent can also give me a positive output like this all the way in quadrant 3. But do I even need to worry about it? Well, let me look at my range. Where did I draw that picture? Yeah. The range of tangent inverse is from negative pi on 2 to pi on 2. That's the first and fourth quadrant. So I don't need to worry about that other angle that can potentially give me this that's all the way in the third quadrant. So theta is just 60 degrees. So you've got to know these special triangles and the ratios of the sides, be able to recognize them. If you see a square root of 3, immediately you're thinking 30, 60, 90 triangle. Just plop one down, see if the ratio of sides is right. If it's not, then write down the other orientation of the 30, 60, 90. Make sure you got your ratio of sides right. I've got my square root of 3 over 1, giving me square root of 3, so I know it's this angle. Then as a last step, you consider the range of your trig function to make sure, or your inverse trig function, sorry, the range of your inverse trig function to make sure that the angle that you found is appropriate and in the range. And once you've confirmed that it is, you can finally write down your answer, which in this case I've already written down, but I'll just to reiterate, tangent inverse of square root of 3 is 60 degrees. Or I could say pi on 3 if I wanted to write it in radian form. All right, I'm going to leave you with D and E. Try them. They will be on exams and homework, obviously. So try these and see what you can do. These are a little bit trickier because, well, you'll see. Try them and see how far you can get. Don't worry if you can't get a final answer, but we will pick up here next time. We're going to go through a few more examples, actually quite a few more examples, all the way up to example 7 for this section. And then we'll spend the rest of whatever time we have on Monday just reviewing. And then the exam will be on Wednesday. So you guys are good to go. If you have questions, you can stick around. I will see you Monday.